Alright, this is Physics 1C for April 23rd. Today we're talking more about Faraday's Law. Just a brief overview of what Faraday's Law states. So Faraday's Law was discovered by a guy named Michael Faraday. He was a British scientist who basically discovered most of the rules that we know about modern electricity and magnetism and how, well, this phenomenon, induction, works. And what he figured out was that basically that you can induce an EMF. We call it E, I, and D for induced. You could call this Faraday's Law of Induction, by the way, if you want to, because it's really just about this phenomenon that we call induction. You can induce an EMF in a coil as long as there is a change in flux through the coil. So it's ddt of flux. And what flux is, to remind you, magnetic flux is defined as, unfortunately, it's this complicated surface integral thing, where you have to find the integral of B dot dA. Now, you've had a lot of experience doing stuff like this because you've done it with Gauss's law a lot, but a simpler way to do it is if the magnetic fields and the area aren't really, sometimes you can just write it like this, basically. Quite often in this class, this is how we're going to be doing it. Sometimes, if the magnetic field varies over the area, okay, and we did a problem like that, so I'm going to remind you because we'll be looking at things like this in the future, and you'll see it on your homework. So if I have a current here, I1, and I have a coil next to it, right? We know that that current in the wire produces magnetic field lines that point in like this. But the thing is, the ones over here are much stronger. The ones closer to the wire are bigger, and then the field gets weaker over time, or sorry, over the distance as you move to the right, farther away from the coil. So in this situation, if I want to find a magnetic flux through my loop right here, this is my loop here, right? That's the area of the loop. We actually do have to use this integral, and we did a calculation with that. You can go back and look at it from a previous class. But quite often we can just do this, okay? Now, what the induction law tells us is that basically any time either the magnetic fields, the area, or the angle between the area and the magnetic field change, you're going to get what's called induction. And we looked at a couple examples of that. One of the examples was, suppose that I have some coil of wire. This is basically what Quincy did in his video. And I take a magnet, right, and I push the magnet into the coil, oops, north, south. If I push the magnet in this direction, there's going to be an EMF that gets induced in this coil. And I can actually tell you the direction of the current. Let's see, I gotta think about it for a second. So the current would actually flow like this. You'd get current in the coil as long as the... That's right, is it? Yeah. And we'll talk about how I know what the direction is there, too. That's using something called Lenz's law, and that's where this negative sign comes from that I haven't talked about yet. Alright, so let's look at an application of this. This application here. Inducing an EMF in a coil. So we'll read this. A coil consists of 200 turns of wire. So N is the number of turns of wire. Okay, and that means we've got some kind of a coil. Each turn is square, so the turns are like this. You know, might as well just use a shape, right? So you basically have a whole bunch of coils that are just kind of wrapped around some kind of a square frame, right? So maybe you can imagine you've got some copper coils that just wrap and wrap and wrap and wrap. You just have coils and coils and coils. All these problems with Faraday's law are always going to be about lots of coils because it's how you get, you know, more EMF. So you've got this metal frame of a coil like this. There's 200 turns. Each side is D, and so the symbol D is equal to 18 centimeters, so that's 0.18 meters. It says a uniform magnetic field directed perpendicular to the plane of the coil is turned on. Perpendicular to the plane of the coil, well, let's just say that it's going into the page then. And then it says, if the field changes linearly from 0 to 0.5 Tesla in 2 seconds, that means that initially this field is equal to 0, and then final, this field is equal to 0.5 Tesla. And then the time that this takes, we'll call that delta t, is 0.8 seconds. And we want to find the magnitude of the induced EMF in the coil while the field is changing. Does the question make sense? This would basically be what would happen if you take a magnet that's not inside the thing and you push the magnet into the coils. So this calculation is going to end up being pretty easy. I'm going to show you two different ways that we can do it. So our actual equation for induced EMF is negative N, and then d phi b dt. Okay? And in this case, we need to calculate the magnetic flux, or in this case, really the change in magnetic flux. But there's this derivative here, right? And if there's a derivative, you kind of need to have, like, you know, you kind of need to have, like, a equation, right? How could I make an equation for the magnetic field as a function of time here? Can anyone tell me what that would be? What would it look like if I plotted it? It goes from 0 to 0.5 in 0.8 seconds. What would that look like on a graph? Positive slope, right? It's going to do something like that, right? We know that here and here, what the values are going to be, right? This is going to be 0.8 seconds, and this is going to be 0.5 Tesla, right? So I could say that the magnetic field as a function of time is just basically equal to the slope, which would be rise over run, right? So that's 0.5 Tesla divided by 0.8 seconds. I don't know what that's equal to. 5 over 8 is like a little more than a half, so it's like, what, 625? So this is going to be something like, yeah, 0.625 maybe? Is that right? Does that look right to you guys? Okay, so then now that we know what the magnetic field is, we can say, okay, well, our induced EMF in the coil, and how is this EMF going to be induced? Well, it means there's going to be a current that's going to flow through this coil as a result of this. We'll talk about that in a second. So the induced EMF is going to be equal to negative N. I'm going to do one more step here before I plug numbers in. So it's d dt. Now flux is going to be equal to the magnetic field as a function of time, multiplied by the area of the coil, and multiplied by the cosine of the angle between the area vector and the magnetic field, which is going to be 0. The area vector, in this case, is also going to point into the board, or into the screen. Okay? So we end up getting... It's kind of hard to read inside of there. Let me just erase what I wrote here. That part, not the whole thing, just this piece. There's what I wanted to write there is B of t. Is that black? I think it is. There we go. That's magnetic field times the area. I don't have to do an integral here because the magnetic field is uniform over the area. It's changing in time, but it's not changing in space. Does that make sense to you guys? Like, the only time you need to use this equation is if the magnetic field changes in space. But it's going to have the same value throughout the entire... See, it says a uniform magnetic field. So it's the same everywhere in space. It only changes in time. Does that make sense? Okay, so let's finish solving this. We've got some numbers to throw in here now. So negative N. Yo, what's up? If the direction of the magnetic field changes relative to the loop, it would be the angle that changes. Yep. What I mean by changing in space is like up here, a non-uniform field, right? In fact, we'll do a problem with that next, maybe, just to make it more clear about what's going on, about like when you would use it, because I know it'll show up on your guys' homework, and I don't want you to get confused. Your textbook doesn't have a lot of problems where you actually do that. We can do one though. Okay. All right, where are we? Okay, so over here, induced EMF, right? Finding the induced EMF. That's equal to negative 200. Turns is not really a unit, so you don't have to worry about that. We're doing ddt. Now, the area is constant. We're just going to pull that out. The area is going to be 0.18 squared, right? It's a square. And then we just need to do ddt of this thing, right? And you can... Oh, this wasn't quite done, was it? Magnetic field is a function of time. That's the slope, but we need to multiply that by t, right? That's the actual equation for the magnetic field as a function of time. My bad. We need to do derivative of this, though. And the derivative of this would just be 0.625, right? Tesla over seconds. And what we're left with then is whatever this calculates out to be. Let me get my calculator. You guys can calculate it too. You know, I really miss being in the classroom. I really do. 200 times 0.18 is 0.18. It's 0.65. I got 4.05. Is that what you guys got? Okay, what's the unit? Well, it's Tesla meters squared over seconds, and I'm going to say that this is actually volts. And I'll prove it here in a second. Oh, that negative sign, right? I was going to tell you that the negative sign is something that you're often not going to worry about. I'll tell you what it means, though. I can actually use this to tell you what it means. Yeah, let's leave it in there, because I don't want to... Yep, there's the negative sign. But what does negative mean? Okay, well, let's talk about what induced EMF is, first of all. Can someone tell me, what is induced EMF? Like, what is EMF? Period. What is it? Yeah, it's voltage, right? So, suppose that I also tell you that this total set of wires right here has an overall resistance, okay, and I'll write it out in case this isn't clear what I'm saying. Let's say that it's a resistance, and it has a resistance of, like, let's say 0.1 ohms, okay? If that's the case, then if I take the induced EMF and I divide by the resistance, that's going to give me the current that's induced, right? Does everyone understand that? So the induced current then would be like, what, negative 40 amps? Or 40.5, whoops. 40.5 amps, right? So, what does that mean? So there's going to be a current. The magnetic field was increasing, right? So what I'm going to tell you is that the direction of the current, and let's use, what's a color that's going to show up on here well? Purple or something. Or I already said blue. This is going to be the direction of the current, that way. I got to make sure before I say it. I'm going to prove to you why it is, or tell you why it is in a second. That's going to be the direction of the current. It's going to flow, what is that? Counterclockwise? So this is where the negative sign comes from. And the reason why I know what direction the current goes is because of this negative sign, okay? So if you point your thumb in the direction of the magnetic field and the direction of the area vector, right? Would you agree that the fingers of your right hand would sweep out clockwise? Take your thumb, put it on your screen, point it into the screen, right? And then wrap your fingers of your right hand. Would you guys agree they go clockwise? Okay. The negative sign tells you need to flip that to find the true direction of the current. So basically, you point your fingers in the direction of the magnetic field. If the magnetic field's increasing, you have to flip your thumb around, and that's going to tell you the direction of the current. It's called Lenz's law. We'll talk more about it, but for now, I'll just say, you get an induced EMF. It happened because of an increasing magnetic field, and so the current in the wire has to set up a magnetic field that points opposite to the direction of the existing field. I know that's a lot of words, but for now, we're just learning about the induction itself and the values, and we'll get to the direction later. Did any of that make sense to you guys? So the negative sign tells you that the current goes opposite the direction of the external field, right? I'll write that down. How if I type it? If I type it, it's going to be a little bit... Let me mute my mic while I type it for a second. I don't have to do that, whatever. Can you guys hear my air conditioning? Okay. That's actually it. And this is like, whoop, that's not what I thought was going to happen. This is called Lenz's law. The negative sign indicates that the induced current flows in a direction opposite to the change in flux. So because the flux in this case was increasing, can you guys see that? In this case, in this problem, flux increased. Everybody agree with that statement? Flux goes up, right? Zero magnetic field, some magnetic field, but that doesn't tell you what flux is, because to get flux you have to also multiply by the area, right? The flux got bigger, so the induced current that's another way of saying Lenz's law. The flux increased, so the induced current has an induced magnetic field opposite to the external field. When the flux increases, the induced current has an induced magnetic field opposite to the external magnetic field. That's what the negative sign means. That's what the negative sign here means. It's just about the direction of the current. Do you guys all understand? That's cool. Let's just leave that confusion where it is, and we'll more formally develop this here in a second. I probably won't even completely get to it today, but let's look at another application, okay? The only way to learn about this stuff is just to keep going, but this is basically what Lenz's law states, and I'm going to give you some examples to clarify that here in a second. But for now, we're going to talk about something a little bit different. It's the same topic, but it's just a little bit different way of doing it, okay? So we're going to talk about motional EMF. The reason why I'm glazing over what Lenz's law is because we need to devote a long period of class to actually talking about it, and it's not important. So the other reason is it's not that important. It's interesting to know the direction, but what really matters is that you understand how the EMF itself is calculated and how you can maximize it, right? Understanding that equation is more important. The negative sign is one small detail, right? Because quite often you don't really care what direction the current flows, if that makes any sense. You don't really care. You just care that there's current flowing, right? So you can power your light bulb, or you can run your computer, or you can listen to your music, or whatever. You just need current for that. It doesn't matter what direction it goes. Okay, motional EMF. So here's what we're going to do. We're going to take a setup. We actually have looked at something like this in the past, but now it's going to be a little bit different than before. So I start off with some rails, okay? These are going to be some kind of conducting rail. Conducting rail. And along this rail, we're going to take a piece of metal. And that metal is going to make contacts at both ends. So it'll form a closed loop. Okay. In addition, I'm also going to say that we can characterize the resistance of our wire. Okay. We're going to say that the resistance is entirely given by just some R right here. So we have some resistance, and that describes really the resistance of the entire loop. Okay. Maybe the wires have very low resistance, and this metal has very low resistance, but nonetheless, you attach it to a large resistor or a light bulb or something like that. Alright. Now, the other thing we're going to need here is we're going to need a magnetic field that points into the page. It could be out of the page, doesn't really matter. So here's our magnetic field. And this magnetic field is going to exist all over the conductor. It's going to be uniform. It doesn't have to be, but we're going to make it uniform. And now what we're going to do is we're going to pull with a force in this direction. We're going to call it the applied force. And we're going to do it in such a way that we pull the bar with a constant speed. Okay? So this bar is going to have a constant velocity. It's going to have a velocity that points in this direction that we're going to call v. And it's going to be a constant velocity. Okay? So the applied force is done in such a way that v is constant. Alright, so just imagine we attach a string to this rail and we just pull it to the right. That's basically what's happening. What's going to happen in this loop of wire here, okay? What's going to happen in that loop of wire whenever I pull this rod to the right? Assuming that these are all electrical contacts right here. And it forms this nice closed loop right here. What's going to happen inside of that wire right there? According to Faraday's law. Yeah, and why do we have a current flow in this case? There's three things you need. One of three things needs to have happen for the. One of three things has to happen for Faraday's law to work, right? Either the magnetic field has to change, the area has to change, or the angle made between the two of them has to change, okay? So which one of these is changing in this case? In a way, you're gaining more magnetic field, but the idea is that B was uniform. I should have said that. You're picking up more magnetic field, but you're doing so because the area is increasing. The area of the loop is growing, right? You guys see that? But I mean, you could think of that if you want to as you're catching more magnetic field, but it's happening not because the magnetic field is changing, but because the area of the loop is growing, right? Now, if we want to actually define something here, what I'm going to do is I'm going to say, let's define this point right here to be x equal to 0, and then we'll label this point right here to be x, okay? And then say that at t equal to 0, this rod, the bar, let's say it started off basically right over here at t equal to 0, okay? If that's the case, and it's being moved at a constant speed, right, then this distance, which we would call x, would be equal to the velocity of the object times the time. Right, would you guys agree? If the rod was over here to the left at t equal to 0, then this distance would just be velocity times time. Is everyone in agreement on that? Did I confuse you guys with that one? Or is that just... that's... what's up? Yeah, simple, right? Exactly, okay. Now let's call the length of this rod L, and let's apply, here. Let's apply, Faraday's law. You know Faraday never used any math, and yet he has this equation named after him? Okay. The EMF that's induced in this coil is going to be equal to N. We'll say N's going to be 1. We're going to say there's just one loop here, okay? And then we have flux. Okay, well, flux is going to be, in this case, ddt, and we're going to say it's going to just be B times A. The magnetic field's oriented perpendicular to the loop, so there's no angle between the area vector. The area is not changing, so we basically just pull that out. But the... oh, sorry. The magnetic field's not changing, so we can just pull that out. But the area vector is, or the area itself is. And what is the area of this loop? Well, if this length is L, then the area of my loop, if it's a rectangle, is basically just L times this, or L times VT, right? So basically the area is equal to L times X at any moment in time, but that's going to be L times V times T, right? If I plug that into here, then I take the derivative. Well, L is constant, velocity, as I said, was constant, and so, you know, you just have a T. ddt of T is just 1, right? So we end up getting negative BLV. That's the EMF. And really, we don't really care about this negative sign. Now, I can tell you what direction it goes. Maybe some of you can predict, based on what I just said, or take a guess. What direction do you think the current should flow here? Oh god, what did I just do? We call this motional EMF, by the way. The negative sign just doesn't matter, though. Counterclockwise. So that would be like this, right? Oh. Like this. Like that. Like that. That is correct. Now, how did you know? That's right. Did that make sense to you guys? Did what do you say makes sense? It's really quick. You're picking that up. Did you read before class? Cool. That's good. No, he's right. I'll scroll back up so you can see what it says. You know, these two things. I feel like this is a better explanation. Just if you consider what it says there, the flux increased, right? Same thing here, right? Flux increased, right? So that means ddt was positive, but there's a negative sign, so you gotta flip it. Point your thumb in the direction of the magnetic field, because it's increasing, you flip your thumb around, counterclockwise. So, here's another way you can figure it out in this kind of problem, by the way. This bar, right, it feels more than just this force, right? What other force would this bar feel, other than gravity or something like that? Don't worry about gravity. What other force would this bar feel as I'm pulling it to the right? What other force does this bar feel? It has to feel more than one force, right? You guys agree? Because the velocity is constant. That's not possible if you only have one force acting on the object. Would you guys agree? You must have some other force opposing this, right? What force is it? You could have friction in the system, and we could talk about friction, but let's assume it's frictionless. It just, that's just an additional detail. It's not super important. What other force might act on a bar that has a current running through it that's inside of a magnetic field? Magnetic force, right? And you tell me with the right-hand rule, if the current flows up, what direction does that force point? You point your fingers in the direction of the current, you face your palm downwards toward the direction of the magnetic field, and then your thumb points in the direction of the current, right? So the force, magnetic force acting on this current carrying wire would point left according to that rule. Would you guys agree? There you go. And it has to be equal and opposite. The F applied, magnitude-wise, has to be equal to the magnetic force, right? And I want you to think about something else. Suppose that the current was actually flowing in the opposite direction. What direction would the magnetic force be? It'd be to the right, right? Do you guys agree with that? If the current was actually flowing down, the magnetic force would also be pointing to the right. Can you guys see that? Okay, so can you also see how that's just kind of ludicrous? The idea would be that if I pull this object to the right, if there was a current flowing down, you get an additional force that would actually accelerate the bar. It would effectively be like getting energy for free. You know what I mean? You just that would imply that you tap the rod and all of a sudden it just accelerates off the end. You see the problem? See how it violates kind of conservation of energy? That's all that Lenz's law is. It's a statement of conservation of energy. That negative sign is a statement of conservation of energy, effectively. You would otherwise be able to violate energy if it was positive. Does that make any sense? Okay, so we know the current flows up. We know the magnetic force goes to the left. We also know how to calculate the magnetic force, right? So if we take this calculation down here, so F applied should be equal to, the magnetic force is equal to I times L times B, right? Well, how do we get I? I is the current flowing through here, and we just found over here that the induced EMF was negative BLV, right? Well, that means that the induced current, I, is basically just the EMF, BLV, divided by R, right? So if I plug that into here, then I'm going to get, what is it going to be? B squared, L squared, times the velocity, divided by R. Oops, getting ahead of myself. That's the applied force. Now, we can also calculate the power that the applied force puts into the system, the rate at which the applied force actually delivers energy into the system, okay? And we get that by just taking the force times velocity. I don't know if you guys remember this, but power, this is power right here, which is the rate at which work is being done, is equal to applied force times velocity. So in this case, that would be this whole thing multiplied by v. So you can see you just get a v squared then, right? This would be basically the power input, right? Because you're pulling on this object and you're putting power into the system. Where does the power go? Where does all that power go that you're putting into the system? Where is it going to? Yeah, this basically moves the charges, right? The electrons. And then, as you say, that then leads to the resistor turning it into heat, right? So, or it can be light, too. Like, if the resistor was just a light bulb, the resistor can be any device that dissipates heat. But that's exactly what's happening. So check this out. I think this is kind of cool. We know the current, right? The power going into the resistor, or the power that's dissipated by the resistor, that's given by I squared R, right? You guys remember that? I squared times R, it's been a while. That gives you the power in an electrical circuit, right? It's the rate at which power is dissipated into the circuit. So the power in that resistor then is going to be this thing squared, right? So you get V squared, L squared, oops, V squared, divided by R squared. But then you multiply by R, so they cancel, so you end up getting the exact same thing, which is pretty cool, I think. Now, there's no such thing as a circuit in which the power that you put in is exactly equal to the power that you put out, because there's always going to be internal friction, as you guys mentioned, but the fact that these are the same in this ideal circuit that we created is kind of cool. You get the same answer either way, right? Whether you use the force equation or whether you just use the I squared R equation. Does that make sense? So this would be called, often this type of device could be referred to as a slide wire generator, because you could basically generate electricity, right? That's what this does. You're generating electricity just by moving that bar right there. You drag that bar to the right, you grow the size of the loop, you generate electricity. It's pretty powerful. Now, the problem is that it's not repetitive. It doesn't continually produce something. That's the advantage of the kind of motional generators that involve rotational motion that we talked about last time. Okay, let's look at an application of what we just talked about. You guys will see quite a few homework problems related to this motional EMF stuff. And that's this one right here. It's a little bit more. Okay. So, a conducting bar. Maybe make this a little bigger. I don't know how well you guys can read this. Conducting bar, illustrated in figure 31.9, moves on two frictionless parallel rails in the presence of a uniform magnetic field directed into the page. The bar has a mass m, and its length is L. The bar is given an initial velocity v initial to the right, and is released at time equal to 0. So released, that's kind of a weird way to say it, but it's basically pushed to the right with this initial velocity. Yep. It's released at t equals 0. Using Newton's laws, find the velocity of the bar as a function of time. Okay. So, what do we know about this? We just figured out that the EMF that gets induced in this system, and let's not worry about the negative sign, is given by B times L times V. We also learned that the current in the wire is given by B times L times V divided by R. And we know that the magnetic force that's acting on this object is equal to I times L times V. We can mix all those together, and as it says, we need to use Newton's laws, right? So let's come over here. We can say net force that's acting on our rod should be equal to the mass of the rod times its acceleration. Okay. The net force on the rod is just going to be this FB thing. And for A, well, let's leave it as A for now. Magnetic force is ILB. That's equal to M times A. All these things we kind of know, right? So I was BLV over R. So this is going to be B squared L squared V divided by R. B squared L squared. I is this. Yeah. Does that look right to you guys? But then we notice that this velocity shows up right here. So I'm going to put over here that the acceleration is actually derivative of the velocity, right? Some 1A things. You guys follow me so far? Now there's one other thing we need to do here, I think. I think we have to do this. I think we need to throw a negative sign in here. No, we don't. The force and the acceleration are in the same direction, right? The acceleration is this way, right? Because it's going to slow down. So I think we're fine. I think this is okay. Alright, our goal is to find the velocity as a function of time. What do I need to do next? Separate variables, yep. So we need to basically get the v on the right-hand side and everything else on the left-hand side, right? So we're going to have dt. Man, I really think I'm going to have to throw a negative sign in here, because dv/dt is going to be a negative. You guys agree? No. There's no applied force. There's no applied force in this equation. But these two things, they are opposite to the direction of the velocity. Let's see what happens when we put the limits in here. It may work itself out. Let's see. So we have dt, and what's left over here on the left? It's dt divided by r times m. And then in the numerator we have b squared L squared, right? And then on the right-hand side we're going to have dv over v, right? Does that look right to you guys? We integrate both sides. On the left-hand side, we're going to integrate from time equal to 0 up to some time that I'm going to call t prime. On the right-hand side, it starts from an initial velocity vi, and we want velocity as a function of time, so we're going to go up to some arbitrary v prime, right? I mean, eventually it's going to stop, but if we put v to 0, we'll be left with no variables left over. You have to have a negative sign in here. This isn't going to work out without it, right? I think because the initial velocity is to the right, and that's it. Either I call this negative. That might do it, actually. Either I call this negative, or I put a negative sign over here. I don't know which one I'm supposed to do. I'm bad at math. What do you guys think? I think this is the way to go then, right? Negative VI. What do you guys think? Okay, let's give it a shot. Let's give it a shot. I think both ways work. Maybe we try both ways. That would mean that basically negative, 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 and now we end up with just a negative sign here, basically, right? I think it works either way. I want to do it both ways, though. Okay, right-hand side, what's that going to be? Natural log, right? Of v prime divided by vi. Everybody agree? And then on the right-hand side, or left-hand side, this just becomes t, right? So we're going to get negative b squared l squared t divided by r times m from 0 to t prime. So that's what we get there, right? And now we raise both sides to the power of e. The right-hand side just becomes v prime divided by vi. The left-hand side becomes just e to the negative b squared l squared over rm all times t prime. And now we're basically done, because now we can say that v prime of t prime is equal to the initial velocity times the e to the negative b squared l squared over rm. I know for a fact you guys have a homework problem that's very similar to this. I can't remember if it's lab manual or what, but it's not exactly the same thing, but I remember you do a calculation where something like this shows up, and you have to solve a differential equation to get there. Anyway, so there you go. The velocity is a function of time, and we can actually, now we can actually get rid of these primes, because we don't need them anymore. They were just dummies, right? I didn't even write it over here, so. It's an exponentially decreasing velocity. We're going to do one more Faraday's Law problem. Do you guys have any questions about this? I call that Motional Emf. Alright, let's look at a Faraday's Law problem. I need to pause for a second. Do you guys have any questions? Am I still recording? Yeah, good. Okay, one more problem. This is the one I kind of alluded to earlier. So, we take a wire, and we say that it carries a current that we call I, but this current varies as a function of time. And over here I'm going to say it's going to be a sine wave kind of thing. So I of t is going to be equal to just some I naught value, we'll pick a value for it in a second, times the sine of some frequency, so omega times t. Now, near this wire is a loop. This loop doesn't carry current initially, but because of the fact that there is a current here that's changing with time, as a result, there's going to be a magnetic field that also changes with time. And we're going to say, you know, it's going to point kind of like this at one point in time, but it's varying sinusoidally, okay? Because remember that a wire, right, will create a magnetic field that is equal to, if it's a long current carrying wire, mu naught times the current divided by 2 pi times the distance that you are away from the wire. So if, for example, I were to draw a line here, and I call it R, then at that location, that's the magnetic field. Okay, and so the goal here is to calculate the induced current in the loop, and I'll give you some values. So we want to that's not how you spell that. Calculate induced current in the loop. Okay. So we've got a sinusoidally varying current, which has the effect of creating a sinusoidally varying magnetic field, right? It varies as a sine wave. So this magnetic field is going to point into the page when the current goes this way, but eventually the current's going to turn around and go the other way, right? Because this current, if you think about it, is going to undergo a kind of effect like this. So sometimes it's positive and sometimes it's negative, right? Which means that the magnetic field's going to go into the page and then out of the page, into the page, out and out and out. Does that make sense to you guys? I want to calculate the induced current in the loop. So, this requires that we use Faraday's law. But, I guess I can ask this question. Does this magnetic field change in space over the loop? Or is it constant over the loop? Does this magnetic field change in space over the loop? Not in time, but at a moment in time. Snap at a moment in time like we are right here. Is the magnetic field over here the same as the magnetic field over here? Or is one weaker than the other one? That's right. So this is an example of the magnetic field changing in space, right? Over the space of the loop, it's not uniform, which means we have to use the full form of the flux, right? We have to use this one. We get to do the exciting action of calculating an integral and then taking the derivative of it afterwards. So let's do that. So in order to calculate the flux through our loop here, what we're going to have to do is we're going to have to, and we did this in a problem before, never hurts to see it again, we're going to have to split our loop up into these little slices, and we're going to say that the slices have a thickness that we call dr, and the distance to an individual slice we're going to call r, and then we're going to say that our dA vector is going to be this thing right here now, okay? So your dA vector is going to be pointing into the page, and this entire thing is dA, basically. Okay, this entire slip thing is dA. It's the infinitesimal area, so it's a tiny slice of area, and I would say that dA, well, you guys can tell me, if we want to know what it is, we need to have some dimensions here, right? So we're going to call this side L, we're going to call this side over here W, and then we're going to call this distance right here A, okay? So what you guys tell me, what would the value of dA be if I have a length L and a thickness dr? What's the area of that? Yeah, in this case it's dr, but yeah, you got the right idea. L times dr, right? So now that's our area vector, and we're going to say that the area vector points in the same direction as the magnetic field. So now when we finish this calculation here, we're going to say n equal to 1. Okay, you can have more loops if you want to, but it doesn't really matter. So it's going to be negative d dt of the surface integral of bdA. But we know what those things are now, so we can plug them in. So it's going to be negative d dt of the integral of b. Okay, well, there's b, but b has I in it too, right? So we're going to put them all together here. We're going to have mu naught multiplied by the current, the initial current, times the sine of omega t, divided by 2 pi r. I think that's everything, right? But we need to multiply this by dA, so all of that's b, and then dA is this, right? LdR. So L and then dr. I'm going to stop for a second. There's a lot of stuff in that equation. Make sure I didn't miss anything. And if you guys have questions, please let me know. We're going to split this. Do you guys have questions? Let's pull all of the stuff out that doesn't change. Well, the minus sign doesn't change too. Minus sign and L we can pull out. And then we have d dt. The only thing that varies with time is the sine function. And it doesn't vary as space, so we can pull that out of the integral. And then we have what's left inside. I think it's just... right? I look right to you guys? So what do we have left? So we have our negative sign, mu naught, I naught, L. When I take the time derivative of this, I'm going to get an omega from the chain rule. The derivative of sine is cosine. Oops. I want to do this integral, but I need limits. The limits are going to be from a to a plus w. So this is going to be the lower limit. That's a, and this point right here would be a plus w. So we're left with this integral is going to go from a to a plus w, and that integral is going to be the natural log of a plus w divided by a. And this is, oops, this is your induced EMF as a function of time. It is a long, messy answer. I'm pretty sure you have a lab manual problem that is extremely similar to this. Maybe some slight variations. I think the difference is in the lab manual problem, the loop is moving or something like that. But it's not that much different, really. That all makes sense. Was that too much calculus? We did a differential equation, then we just did this surface integral thing. We had that early easy problem, but it's a lot of stuff, I know. What does that answer even mean? what does this whole junk here even mean? Well, it says that the induced EMF in our wire has a negative sign and it varies like a cosine function right here, right? So that means that you're going to have an induced EMF in this wire that sometimes is going to point in one direction and other times it's going to point in the opposite direction. But you're going to have a current that's induced in this. It's going to flow, let's see, when the current's flowing this way, well, it's going to depend, because sometimes the flux is going to be increasing and sometimes it's going to be decreasing. If it were on the rise of this first curve right here, the flux is increasing, so you're going to get an induced EMF that's going to be opposite, like this. And you can even plot what the induced current's going to be, right? Because it's basically just a cosine function, right? So if we plot it right underneath the other one over there, right, if I take my thing and I plot, it's a negative cosine function, right? So it's going to start down here. It's going to do this. This is the induced current. They're going to be kind of out of phase with each other, right? This is going to be the induced current. When the current in the... when this current, right, is at 0, the current in the induced... the current in the loop is going to be negative. Whenever this reaches a maximum, right, the current in the loop is 0. Whenever it gets 0 again, you're back at a maximum, right? Because the slope is maximum. That's basically what we're plotting here, right? The induced EMF is basically just the slope. It's the inverse slope. There's the inverse derivative, right? Okay. Does that make sense? Are you guys lost? Please ask questions. No? It's all perfectly clear? Sure you will. You'll have to. It's on the homework. You'll figure it out. But you can always come back and watch this video and see what we did here. Like I said, I think the one on your homework... I have to pull it. Let's see if I can find it. I think it's 1273. Yeah, the only difference with 1273 is that the loop is moving. I was right. So basically, you take the exact same thing, but you make the loop move. And because the loop is moving, this is a little bit of a hint of this. This distance is changing. This is changing right here. Just to give you an idea of what's going to happen on your guys'... I'll just show you. I'll show you what would happen. So imagine now that we add to this exact same problem the fact that the loop moves with a constant velocity. Okay? And let me just show you how this line right here would change. It's only this line that would change. You guys see what I'm saying? All we're going to change is we're just going to make it so that the object moves with a constant velocity. The whole loop. You're dragging the loop. Does that make sense? Okay? So here's what's going to change. This derivative is going to act on both terms. So we'll show you what I mean. We're going to have to take the derivative of both terms, and what's going to happen is that a is now going to be a variable. Okay? So a now is going to be equal to something like the velocity times the time. Does that make sense? So when you do the derivative, and then I think you just replace a with vt. So we replace the a here with v times t. W is just the size of the loop, so it doesn't change. And now you need to take the derivative of that. So you gotta do what? You gotta do like a chain rule, right? Not chain rule, sorry, a product rule. You have to do... Yeah. Does that make sense to you guys? It's not much different, right? I'll let you work out the details of what the answer is. Still make sense to you guys? Okay, I'm stopping the recording right there, but I will stick